Welcome to the lecture series on CFD, Part 1. This is Lecture 13 on Introduction to Solution Methods for Unsteady Flows. This and the next two lectures are devoted to solution methods for unsteady flows. After a brief introduction to flow unsteadiness, the simplest time marching schemes introduced by Euler more than 250 years ago will be described. The explicit scheme is never used, but the implicit version is available in each CFD code. Next, midpoint rule for time integration is described with a focus on the leapfrog method, which is derived from midpoint rule approximation. This method is not offered by general-purpose CFD codes, but it is used in the meteorological community. Trapezoid rule and the Crank-Nicolson scheme are described next. This second-order scheme is an equal blend of the explicit and implicit Euler schemes and is widely used in research codes. One of the most widely used second-order schemes is the quadratic backward scheme, which is described next. It is fully implicit and stable even for large time steps. All major CFD codes offer this scheme for time-accurate simulations of unsteady flows. In addition to the description of each scheme, their application to the one-dimensional generic scalar transport equation is also analyzed. In previous lectures, steady-state problems were considered. However, most problems involving flow and related phenomena are unsteady, also called transient. Unsteadiness can be caused in two ways: by unsteady boundary conditions, for example, periodic or pulsating variation of inlet conditions, or through inherent unsteadiness. For example, turbulence or vortex shedding, due to the nonlinearity of the Navier-Stokes equations. Sometimes flows are statistically steady, and we can use physics-based models to convert an unsteady problem for instantaneous variables to a steady-state problem for time-averaged variables. An example are turbulence models. If unsteadiness is important, we must solve equations which include the unsteady term. How this can be done is shown in this and in the next two lectures. If we try to use a steady-state approach to a flow which is inherently unsteady, we will not be able to obtain a solution. The residuals will oscillate forever, or iterations may even diverge. In unsteady flows, variables vary in general in three spatial dimensions and in time. Time can be considered as the fourth dimension. Variations in time and space are of a different nature. A force at one location in space can influence the flow everywhere around that location. This is an elliptic nature. Forcing the flow at one instant of time affects only future flow development, in principle everywhere in space, but only forward in time. This is parabolic nature. Time discretization can be viewed in two ways: as discrete points in time at which time derivatives are approximated using finite differences, or integration of equation over a time period delta t to reach state at tn plus delta t, which is a finite volume approach. The resulting equations to be solved are the same in both cases. Methods for computing unsteady flows are based on the same principles as methods applied to initial value problems for ordinary differential equations. We therefore first consider the first-order ordinary differential equation, given here, with an initial condition. All transport equations can be cast into this form by moving all terms other than the rate of change term to the right-hand side, that is, the function f contains convection, diffusion, and source terms. We integrate the above equation from time tn, at which the solution phi n is known, to time tn plus 1, to find the solution at the new time level n plus 1. The left-hand side of the equation can be computed exactly, resulting in the difference between the new and the old value of phi. However, because we cannot integrate the function f over time analytically, numerical integration is necessary for the right-hand side. The same methods presented for surface and volume integrals in lecture 7 and 8 can in principle be used. Some examples are presented in the following slides. If the integral is approximated by multiplying the function f at the start of integration interval by the time step delta t, we obtain the explicit Euler method. The approach is illustrated in this figure. The integral of f over time step delta t is approximated by the gray area, whose height is the value of f at the all-time level Tn. Because all values at the right-hand side are from previous time step and thus known, the new value can be computed directly. There is no need to solve an algebraic equation system. If the integral is approximated by multiplying the function f at the end of the integration interval by time step delta t, we obtain the implicit Euler method. In this case, the function f cannot be computed beforehand. One needs to solve an algebraic equation system as in steady-state problems. The only difference is that the main diagonal element in the matrix and the right-hand side are extended by contributions from the unsteady term. It is obvious that the errors for both approximations of the integral of f over time step delta t halve when the time step is halved. Thus, they are first-order methods. Such methods are not suitable when a time-accurate simulation of an unsteady flow is required. The first-order error term has a similar effect in time as was the case with numerical diffusion associated with first-order approximation in space, as demonstrated in lectures 4 and 7. The explicit Euler method is only conditionally stable. The stability limit is severe and makes the scheme useless. The implicit Euler method is unconditionally stable even for very large time steps. It is therefore used when marching toward a steady state is required or when the unsteadiness is very weak. Although the explicit Euler method is practically never used, it is worth checking its properties to understand why. Let us see what happens when the method is applied to one-dimensional unsteady convection diffusion equation for a generic scalar variable phi. When convection and diffusion terms in this equation are discretized with central differences, the explicit Euler method leads to the following expression on a uniform grid. All terms on the right-hand side are computed using values from the previous time step Tn. The following dimensionless parameters can be introduced. The first is associated with diffusion and the second with convection. D is the ratio of time step delta t over the characteristic diffusion time rho times delta x squared divided by diffusion coefficient gamma, which is roughly the time required for a disturbance to be transmitted by diffusion over a distance delta x. C is the ratio of time step delta t to the characteristic convection time delta x over velocity u, which is the time required for a disturbance to be convected over distance delta x. In terms of D and C, this equation transforms to this one. The parameter C is called Courant or CFL number. It is an important parameter in CFD. Assume that phi is temperature. By virtue of diffusion, an increase in temperature at any of the grid nodes I-1, I or I+1 at time Tn should lead to an increase in temperature at node I at time Tn plus delta T. By virtue of convection, when the velocity u is greater than 0, an increase in temperature at grid nodes I-1 or I at time Tn should lead to an increase in temperature at node I at time Tn plus delta T. This means that, to be faithful to nature, the coefficients multiplying all variable values at neighbor nodes in the equation at the bottom of previous slide should not be negative. If some of the coefficients become negative, stability problems are likely. This can be confirmed by von Neumann stability analysis. See section 631 and references in the book. Let us inspect the discretized equation again to see if some coefficients can become negative. To avoid negative coefficients for all values at nodes I and I+1, the following conditions should be satisfied. D should be smaller than 0.5 and C should be smaller than 2D. The first condition imposes a limit on the time step, given by this expression. The method is thus conditionally stable. The problem is that if grid spacing is halved, the time step must be reduced by a factor of 4 for the stability condition to stay satisfied. This condition is severe when wall boundary layers are resolved with a small grid spacing or when elsewhere small cell size is necessary. The second condition requires that the Self-Peclet number should be smaller than 2. This is a sufficient but not always necessary condition to avoid oscillations in solution when using central differences. One example of such oscillations is shown in slide 17 of lecture 6. Let us see what happens if the convection term is discretized using first order upwind scheme. In this case, the following discretized equation results. After introducing parameters d and c, the equation reduces to this form. Now only one coefficient multiplying 5 values from previous time step, underlined with a red line here, can become negative. To prevent that, the following condition should hold. This means that when the convection is negligible, d should be smaller than 0.5, which was also the case when central differences were used for convection term discretization. When diffusion is negligible, the above relation reduces to the requirement that the current number c should be smaller than 1. The use of upwind scheme for convection improves the stability in the case of negligible diffusion, for example when solving Euler equations, but the accuracy is reduced to a level which is too low for practical applications. When convection and diffusion terms in this equation are discretized with central differences and the implicit Euler method is used for time integration, the following expression is obtained on a uniform grid. In terms of dimensionless parameters d and c, the equation reduces to this form. Now the new solution at node I depends directly only on one old value, that at the same node I. Indirectly, the old solution at node I affects also new values at neighbor nodes, I-1 and I+1, but because the coefficient multiplying the old value is positive, there are no stability-related problems. The scheme is unconditionally stable even for very large time steps. However, new values at all grid points influence each other. We need to solve an algebraic equation system to obtain the solution at the new time level. The algebraic equation at node I looks the same as in the case of a steady state problem, that is, for the equation without an unsteady term. The matrix coefficients are given by these expressions. The difference to the steady state equation is that the coefficient at the main diagonal AP and the right-hand side contain contribution from the unsteady term. These contributions are underlined in red here. In general, the right-hand side can contain other source terms like pressure and gravity terms in the momentum equations. We have seen in lecture 7 that midpoint rule is widely used to approximate surface and volume integrals. Why not using it for time integration as well? If we multiply the value of the function f at the middle of the time integration interval by the time step delta t, we obtain the midpoint rule approximation as indicated in this figure. Because the solution is not available midway between the two time levels, an approximation is required to compute the function f at the midpoint. If we use linear interpolation between values of f at the two ends of the interval, we convert midpoint rule to trapezoid rule. This leads to the Crank-Nicolson scheme, which is described in slides 17 to 20. There are two other less obvious ways of using midpoint rule for time integration. One is to integrate over two time steps, from tn minus delta t to tn plus delta t. Now tn is in the middle of the time integration interval, and the use of midpoint rule leads to the following expression. This is an explicit scheme called leapfrog method. The new solution at time level n plus 1 is equal to the solution at time level n minus 1 plus the function f at time level tn multiplied by 2 delta t. We are marching in steps of delta t, so integration intervals overlap. When convection and diffusion terms in this equation are discretized with central differences and the leapfrog method is used for time integration, the following expression is obtained on a uniform grid. In terms of dimensionless parameters d and c, the equation reduces to this form. The scheme appears to be unconditionally unstable because the coefficient of phi n is always negative. This is indeed confirmed by von Neumann's stability analysis. However, when diffusion is negligible, for example when solving Euler equations, the scheme is stable when the current number is smaller than 1. Because the scheme has some good properties, numerous tricks have been devised to improve its stability. The aim is to redefine the old solution. Well known is Dufour-Frankel modification, which replaces phi n by an average of phi n minus 1 and phi n plus 1, as well as various versions of Robert Asselin time filter, based on a central difference approximation of the second derivative of phi with respect to time computed at Tn. See section 6.3.1.2 in the book for more details and references. When time integral of the function f is approximated by multiplying the average of its values at the beginning and end of the integration period with time step delta t, we have the trapezoid rule, shown graphically in this figure. This approach is known as the Crank-Nicolson scheme. This is a second-order approximation of time integral. This can be proven by using the Taylor series expansion as follows, using the shorthand notation Fn is equal f of Tn and phi n. We first write a Taylor series expansion around the time level Tn, and then use it to express the function value at the new time level. From this expression, we can derive an expression for the first derivative of f with respect to time, which is given then by this expression. We then perform the integration of the function f expressed via Taylor series expansion over a time interval delta t from Tn to Tn plus 1. H stands for higher order terms. We then substitute for the first derivative of f with respect to time the expression derived at the end of the previous slide. After sorting all terms out, we obtain the following expression. The blue frame part is the Crank-Nicolson approximation. The red frame part is the local truncation error, which is proportional to the time step cubed. However, for a finite time period, we must take into account that the error is incurred in every time step, and the number of time steps is inversely proportional to time step size. Therefore, the Crank-Nicolson method is a second-order scheme. When convection and diffusion terms in this equation are discretized with central differences, and the Crank-Nicolson method is used for time integration, the following expression is obtained on a uniform grid. We see that the method is essentially an equal blend of explicit and implicit Euler method. It is stable, but oscillation in solution may occur if time steps are too large, which is problem dependent. Because the scheme is essentially implicit, an equation system needs to be solved to obtain the solution at the new time level. The algebraic equation at node I looks the same as for implicit Euler scheme. The difference is in the coefficients and the right-hand side, which are shown in the next slide. The expressions for coefficients in terms of dimensionless parameters d and c are given by these equations. The term qt needs to be saved separately from a possible source term, which may depend on the new solution and thus require updates during the iterative solution process. The implicit and explicit Euler schemes can be blended with a blending factor theta different from 0.5, which gives the Crank-Nicolson scheme. For theta smaller than 0.5, the scheme is unstable. Values slightly larger than 0.5 are used to avoid oscillations, between 0.52 and 0.6. Another possibility to use the midpoint rule to approximate the time integral of the function f is to perform integration over an interval centered around the time level Tn plus 1, as indicated in this figure and by this equation. Now the left-hand side cannot be integrated exactly as in previous methods. An approximation for time derivative must be used. From a parabola fit through the solution at three time levels Tn minus 1, Tn, and Tn plus 1, the following second-order approximation is obtained. See also slide 10 of lecture 6. By applying midpoint rule approximation to time integrals on both sides of this equation, we obtain the following expression. Using the approximation of time derivative of phi defined in previous slide, this equation can be rewritten as follows. K is needed if time steps are not constant. See section 624 in the book for further details. When convection and diffusion terms in this equation are discretized with central differences and the quadratic backward scheme is used for time integration, the following expression is obtained on a uniform grid. The resulting algebraic equation is the same as for the implicit Euler scheme, only the coefficient at the main diagonal and the contribution to the right-hand side are different. The implicit Euler scheme does not have this contribution from time level Tn-1. Here is 1 instead of 2, and here is 1 instead of 3/2. The scheme cannot be used in the first time step. Usually, implicit Euler method is used to start the computation. This scheme is very popular and is available in all major CFD codes. Here is a summary of this lecture. Explicit first-order Euler method is practically never used because of a severe limit on the time step size for stability reasons and because of low accuracy. Implicit first-order Euler method is used when time accuracy is not essential, for example, marching toward a steady state or weak unsteadiness. For a time-accurate simulation of unsteady flows, methods of at least second order should be used. Crank-Nicolson method is a popular second-order scheme. It can create oscillations in solution if time step is not sufficiently small. Quadratic backward scheme is another popular second-order method for time marching. It is fully implicit, that is, convection and diffusion fluxes and the source term are evaluated only at the new time level. This makes it possible to change the grid at one time step. It is only necessary to map the solution from two time levels onto the new grid.